Now we want to talk about the meanings of this eigenvalue. You have these eigenvalues of AG, and let's just focus on the algebraic symmetric first. And what are the meaning of this eigenvalue? First, this mu1 is roughly measures how dense the graph is. Meaning that it has tendency that if G has more edges, then mu1 tends to be bigger. If G has less edges, more sparse, then it tends to be smaller. That's kind of you already have such an intuition from this Rayleigh quotient. It's a Coulomb-Fisher theorem. So roughly, the Rayleigh quotient, or let's say you have X, this Rayleigh quotient gives the number of edges inside of X, which is twice the times number of edges in this, in the subgraph of X. Because here, everything is counted twice as we defined it last time. So technically, you have to write it as this way. So, from this Coulomb-Fisher theorem, this hints that you get the intuition that this lambda 1 is related to how big this is. In fact, we can actually prove that this lambda 1 is at least the average degree and most the maximum degree. Because that we have defined this average degree of G as the average of the degrees of the vertices, which is same as twice times the number of edges divided by n. So, what? The lower bound is easy. Both are not difficult, but the lower bound follows from the Rayleigh quotient. So what do we do if we take the Rayleigh quotient for the all-one matrix, all-one vector? So this vector is the characteristic vector for entire vertex set. Then what do you get? If you consider this, then what? Coulomb-Fisher theorem says that out of all vectors, you take the maximum of this, then you get the mu1. But this is one specific choice. But this is what? You just compute this, and this is twice times the number of edges in there. Maybe, without going through here, this is what? E of entire vertex set, which is what? Twice times the number of edges divided by n. So the bottom part, this is all one vector, so you get n. So you have this inequality. Okay? So this shows it. And then to prove this other one, we consider vector u1. The eigenvector corresponding to this mu1. And what we do, we choose I so that the index I or vertex I, which has the this vector, I's j coordinate, you write down this vector, you have this coordinate, you choose the one with the biggest value. And what? You may assume that this I's coordinate is positive. Why? If not, take negative of this vector instead. So this eigenvector, I mean, it's negative if you just flip every sign. And this is still eigenvector, so you can choose whichever one. You choose the one so that this maximum value is actually positive. And what do you get? This mu1 is nothing but you take the, the ith coordinate and ith coordinate. So you compute this, then that's what? That's mu1 times u1. And then its ith coordinate and ith coordinate are just differ by mu1 on multiplication. So you have this equality. On the top, you can actually compute it. That's what? It's ij times u j, you sum up with all j, but this survives only when ij are adjacent. So you consider all the j which are neighbor of y, and you add the jth coordinate, and you get this. Okay, but what do you know? So this was the biggest one. Each term here is at most this. So this is just what? So how many times did we add this? The degree of I many times, and then each term is smaller than this. So this is smaller than di. And then it's at most the maximum degree of g. So this proves the inequality as well. Moreover, by analyzing this proof more closely, what we get is that if G is connected, and if this mu1 is same as the maximum degree, then this G is a regular graph. Why? You just go through this proof again. If this holds, then what do we have? This and this have to be equality. And this being equality, so here you add degree many terms, and then here you have one term. All of them is at most, it's not larger than this one term. So equality means that every term here is same with this term. That means for I, it's all of its neighbor j have the same value in this eigenvector. And using that G is connected, that shows that from one entry, and these two entries are same, these two entries are same, we keep going to show that every entry in this eigenvector is same. Then this eigenvector is a constant eigenvector. And constant vector is an eigenvector. Then from there, you can deduce that you can deduce that your graph must be regular. Okay. All right. Yeah. Or you don't have to deduce its eigenvector. So from there, it's all same. These are all same. Then what? This degree of I is exactly same with this. And then you do the same thing with for its neighbor j. Then again, you can show that the degree of j is exactly delta of g, and you can keep do that. Because as you mentioned, if is chosen to be maximum, and then its neighbor j, by our argument, have the same value. So you can instead choose j here instead of I. And then you go through, then degree of j is also equal to the maximum degree. So by you keep do that to all its neighbor until you show that every vertex have the same degree, because this is connected. Okay. So this inequality holds And somehow this is like every degree. We get that. We get the intuition from this, using this Rayleigh quotient. We show this inequality, and then somehow we expect that those two are similar, but there are certain distinctions between these two. One is that we want to show that the following difference between these two. The removal of a vertex does not increase mu1. We want to show this. Before we see, it's easy to see that this every degree, once you remove a vertex, it may increase. For example, if you have a very dense graph and then one isolated vertex, and you just remove it, then every degree actually goes up. Number of edges is the same, and the number of vertices is smaller, so every degree goes up. But for mu1, it doesn't happen. We want to show this. If this mu1 is inherited, then we can use this to prove the relationship between the chromatic number and this mu1. For that, let's prove this. Something called Cauchy's interrelating theorem. So this theorem will give us this statement. So let A be an n by n real symmetric matrix. And let's say P be a principal submatrix of A of dimension n-1, meaning that if B is obtained from A by deleting a row and column, which are the same one. The ith row and ith column. Then what? We have the following inequality. So the eigenvalues interlace, where this alpha 1 to alpha 2 are in order eigenvalues of A, and beta 1 to beta minus 1 are eigenvalues of B, then they interlace. So in order, if you write it, then it alternates. Okay, the proof is not difficult. It's, simple. So let's say, assume P is obtained from A by deleting first row and column. So, you can do that because the ordering on the vertices are not important one for us. And by the Coulomb-Fisher theorem, what we have is this alpha k. If you take the maximum out of all k-dimensional subspace, you take the vector in here, which minimizes Rayleigh quotient. And what do we have? The beta k. You do the same thing, but now you take this subspace in subset of R to the n-1 with a dimension in K, and you take the gain minimum of all these ones in here, and you compute the Rayleigh quotient of B. But what does it become same? So you do the same thing, but this B is simply you delete the first column and first row of A. So you write down a column vector. Instead of just writing this X, you attach this 0 at the first one and then write down the remaining column vector. Let's write it. It's row vector, sorry. So it's 0 and X transpose, then 0, X. So these two are same. But what do we know? The last expression is at most alpha k. Why? This is what? This is taking maximal over a restrictive family of subspace. So this is maximum over some restricted subspace, restricted families of subspaces. So that this is over all possible subspaces, and this is for the restricted one. So this is at most alpha k. Yeah. Give me a moment. Let me. Yeah. So you just consider the k-dimensional subspace whose first coordinate is 0, 1 in R to the n. So this is same as what? Maximum over all SR with dimension is k, and first coordinate, so it's S is orthogonal to the 1, 0, 0, 0 vector, and then you do the minimization inside. So you get this inequality. And you repeat this argument for minus A and minus B, then we get the beta k is at least alpha k plus 1. Because so here it's comparing these two, and that. By flipping, you compare these two, and these two, so you get the other inequality. So that proves this Cauchy's interlacing theorem. In particular, if you just care about this first one, then you get this. If you remove a vertex from a graph and you get a smaller graph, it has new eigenvalue, which does not increase. From that, we can prove the following theorem. So Cauchy number of G is at most the floor of mu1 plus 1. So we know that from grid coloring, this is at most the maximum degree plus 1. But once you replace with the average degree, it's never true. But replacing with the biggest eigenvalue is possible. I mean, often this is called the spectral radius. But anyway, so this is what? we know that this is between these two values. And this cannot bound the chromatic number, but this can bound. I mean, if you add 1. But this also can bound the chromatic number. So somehow it shows that it has completely different behavior from the average degree. And proof is easy. We use induction on the number of vertices. The base case is trivial. So when you have one vertex, it's trivial. And assume that this is all true. Assume this holds for n-1 vertex, correct? Then what do we know? As we know that average degree of G is at most mu1. So there exists a vertex I such that its degree is at most average degree, and then which is smaller than the floor of mu1. Then let S be the vertices you get from the graph by deleting I. Then what? And Cauchy's interlacing theorem implies that this G bracket S has the largest eigenvalue and most mu1. So by induction, induction hypothesis is that this induced subgraph can be colored using this many colors. And what we take such a coloring and extend it by giving a color to this eye with some color in it. So this is that this desired inequality holds. Okay. So this mu1 is related to how dense the graph is. And this mu2 is related to some connectivity, say connectivity of G. Related to. It's not same, but related to. How? The following theorem give you that. I mean, this is a theorem called Perron-Frobenius theorem. So this is also useful to get something about the eigenvector for the largest eigenvalue. So this one, if G is irregular, then it's easy to take that this is a constant vector. The largest eigenvector is constant. But otherwise, I mean, it may not be constant, but in some cases, it's good to have some information about this vector, and that's provided by the following Perron-Frobenius theorem. So let G be a connected graph with adjacency matrix A. Then what? Again, mu1 to mun is the eigenvalue. And the largest eigenvalue, U1, has a eigenvector which is strictly positive. So the eigenvector corresponding to the largest eigenvalue, U1, if you see it, every entry of it is positive. Moreover, we have U1 is at least negative for mu(n), and U1 is strictly bigger than mu2. So this is one important theorem because in many cases the eigenvector corresponding to the largest eigenvalue is quite useful, and knowing some information about this is also quite useful. And then this shows that if you have a connected graph, you can find the strictly positive such eigenvalue. I mean, such eigenvalue has all the entries strictly positive. Moreover, this inequality also holds. The proof of this theorem is not too difficult, but I mean, yeah, we will omit the proof because, I mean, I want to cover more things rather than just providing a proof of this. But one of the implications of this is that if G is connected, then mu1 is strictly bigger than mu2. But the other direction doesn't hold. For example, if G is Kn union disjoint union with Km, then you can easily see that all one vector in one, and give me a moment. Yes, in that case, you can easily check that your biggest eigenvalue is, let's say, n is bigger than m. This is n and this is m. But this is disconnected. So connected implies this inequality, but the other does not hold. But the main reason why this direction does not hold is that here the degrees are bigger and here the degrees are smaller. So this is not regular graph. So you can actually check that for regular graph, this direction holds. And in many cases, if you deal with some problem, and then if you use some adjacent symmetric to deal with the problem, then problem is very naturally correspond to the adjacent symmetric. You can solve it if the graph is irregular. Otherwise, if it is not regular, some problems occur. So to resolve that issue, the Laplacian was introduced. Laplacian is somehow, I mean, normalization in a sense that for non-regular graph, you want to do the similar thing that you can do for regular graph. So for regular graph, you use this adjacent symmetrics to solve certain problem, but this technique does not work for non-regular graph. And for non-regular graph, is there a way to save in this argument? Then, if you do this kind of, thing, then you encounter that many cases, if you use Laplacian, then you can save such an argument. Of course, you might get weaker result, but lots of proof technique here for irregular graph using this adjacent symmetric can be done with the Laplacian for non-regular graph. So, what you can prove is that because that your Laplacian, the smallest eigenvalue is 0. Let's say these are the eigenvalues of the Laplacian LG of n vertex graph G. Then lambda 2 is bigger than 0 if and only if G is connected. So we can prove this. So if G is disconnected, then how does this Laplacian looks like? You can actually, from this definition, you can write this metric in this two block for some graph for say P1 and P2, which are the union of some components of G. So we have two eigenvector. So this is all one vector. So 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1 with the right number of 1 and right number of 0 for the eigenvalue 0. So we know that 0 is the smallest eigenvalue. And then if you have at least two such an eigenvalue, and first two, this one also corresponds to 0. So this is 0, this is 0. That means lambda 2 is 0. On the other hand, assume G is connected. And let's say X is an eigenvector of L for the eigenvalue 0. Then what do we have? You consider its Rayleigh quotient. Then what? Using the definition of L, you can check that this is same as this. I mean, this is just nothing but the rewriting of what we have written before, where yes. Here, Aij is 1, only if and only if you have an edge, right? So this and this was same. In the same way, you have this. And what? In that case, this is 0. This shows that this xi and xj are same for all edges of G. As G is connected, this shows that if x is a constant vector, as the eigenspace of the eigenvalue 0 at dimension 1. That means lambda 2 is bigger than 0. So this lambda 2 is actually, I mean, yeah, tells you whether the graph is connected or not. And due to this lambda 2 is often called the algebraic connectivity of this G. It's also known that this alpha 2, lambda 2 is at most the connectivity of G. So this provides the lower bound of the connectivity. Okay, so we have seen the meaning of mu1 which is roughly showing how dense the graph is. Then we have seen the meaning of lambda 2, which roughly is like connectivity of G. So this is from Laplacian, mu is from the adjacency matrix. Okay, so next time we will talk about the, other properties. So eigenvalues are also related to, other concepts such as walks in graph. The walks are the, what we defined before. So we will move along the edges from vertex to other vertex. And then that's also related to eigenvalue, and we will talk about that in the next video. Okay, thank you for listening. I will see you next time.